Okay, in this video I'm going to try and introduce what do we mean by an inner product. So an inner product is going to be a function that sends two vectors to a real number. So the input is a pair of vectors, the output is a real number. Don't worry about this for a second. Let's look at an example, which is the dot product. The dot product, we have two vectors coming in and the output is a single real number. So our notation for inner products is going to be a little funky. We're using u and v with angle brackets next to them. The reason we're using a different notation is so that we don't confuse ourselves with the other kinds of products we have, dot products and cross products and scalar multiples. So we're going to use this new symbol to mean a new inner product. So we've already seen the inner product, the dot product on r to the n. What we want to talk about it now is what kind of inner products could we define on other vector space? Like, could I define an inner product on a set of polynomials or on a set of matrices? If I was going to do it, we need to have some of the same things happen that happen for dot products. So we have more axioms that are supposed to happen or are supposed to be true. So first of all, if you take an inner product of u with v, it should be the same as the inner product of v with u. Same as with the dot product. If you switch the order, you should still get the same answer. And then these next two are basically saying that it's essentially linear. We behave nicely with sums and scalar multiples. And then the last one is kind of specific to the dot product and the inner products, is that the dot product should always spit out a positive number if you're taking a vector dot product itself, because that should be somehow related to the length of that vector. And so the inner product should have this same kind of thing. The inner product of a vector with itself is going to be a number that's greater than or equal to 0. And the only way for it to be 0 is if you're taking 0 dot product 0 or 0 inner product 0. Okay, so a lot of babbling. Let's look at a real example. I'm going to look at this one, the set of 2 by 2 matrices. And for two particular 2 by 2 matrices, u and v, we're going to define their inner product as multiplying the top left corner, multiplying the top right corner, multiplying the bottom left, and multiplying the bottom right. Okay, so this looks really similar to a dot product, so it's not going crazy out of the box, but it is still a function whose domain is two particular vectors and the output is a single number. So as an example, if I wanted to take an inner product of, say, 3110 with 42 minus 1, then according to this definition, we would have to multiply a times e, which would be 3 times 4, plus b times f, which would be 1 times 2, plus c times g, 1 times negative 1, plus d times h, which would be 0 times 1, which looks like 12 plus 2 minus 1, which is 13. Okay, so something to point out is that your inner product is not always going to be 0, but if I take an inner product of something with itself, it should always be 0. So even though we did see some negative numbers popping up, if I had done this vector with itself, I think there wouldn't actually be negative numbers. So let's check one more example of an inner product. Okay, so multiply the top left corners, multiply the top right corners, multiply the bottom left corners, and hopefully you'll see now why there's not actually going to be any negatives, because the negatives are canceling out. And then bottom right corners, which gives us 16 plus 4 plus 1 plus 1, which is 22. Okay, so an inner product of a vector with itself should always be a positive number. Okay, let's see, inner product of 0 with itself should be 0. I think that's probably true. If every one of these was a 0, our answer would just be 0. I'm not going to check all of these, but if you plugged in a, b, c, d, and e, f, g, h into each one of these, you might need to come up with a third vector, a w. The left-hand side and the right-hand side should spit out the same particular real number. So this is going to define an inner product. We'll see some other examples in the following videos.